All right, let's dive into a pretty wild idea today. What if everything you see around you, the stars, this planet, you yourself, what if none of it is made of separate little particles? What if it's all just the behavior of one single underlying thing? I mean, forget everything you think you know about particles, forces, and spacetime being these separate building blocks of the universe. The idea we're digging into today suggests something way more unified. It says that everything, from the tiniest quark to the biggest galaxy, is just a different ripple, a different shape of one single object. So what is this one object? Well, the theory proposes that reality is basically one continuous, three-dimensional fabric. And get this, it's not a bunch of things existing in space. This fabric is the space. It is the matter. It's the whole shebang, all woven together. And the implications of that are, well, they're huge. Instead of needing one theory for gravity, like general relativity, and a totally separate one for particles, like the Standard Model, this idea says they're all just different behaviors of the exact same fabric. It's wiggles, it's stretches, it's dense spots. That's all physics is. It's a search for a complete mechanical blueprint for reality itself. Okay, so if reality is the single fabric, what's it made of? What are its fundamental properties? The theory suggests it all boils down to just four basic characteristics. And amazingly, these four things might be all you need to build the entire universe we see. First up, and this is the most straightforward one, the fabric is three-dimensional. And why three dimensions? The reasoning is actually beautifully simple, because everything we have ever seen, touched, or experienced is in 3D. It's an explanation that starts not with complex math, but with our own direct perception of the world. But wait, what about the fourth dimension, right? What about time? Well, in this model, time isn't actually part of the fabric structure. Instead, time is just what we perceive as the fabric constantly changing its shape. It's not a place you can travel to. It's just a measurement of the universe's endless motion.
Second, property. The fabric isn't the same everywhere. It has a variable density. Just imagine some parts can be more scrunched up and substantial, while other parts are more spread out.
And this is where it gets really clever. Those denser, more scrunched up regions of the fabric, that's what we experience as mass. An object that has more mass is, in this view, just a region where the fabric of reality itself is denser. And this variation in density is also what gives rise to gravity. Simple, right? The third property is elasticity. So this fabric can be stretched, it can be compressed, and crucially, it can carry waves. Think of it kind of like a cosmic trampoline. It can ripple and vibrate when you poke it. But here's the key. That elasticity isn't infinite. The fabric has a certain stiffness to it, a natural resistance to being stretched or squashed. And that resistance creates a natural speed limit for any wave traveling through it. What is that universal speed limit? Well, the theory proposes it's what we call the speed of light. Now think about that. In standard physics, the speed of light is just a given, a fundamental rule. Here, it's a consequence of the fabric's physical stiffness. And that brings us to the fourth and final property, a limit on how sharply this fabric can be curved. You can't just fold it into an infinitely sharp point. There's a physical limit, a maximum bendability. This is the idea that really builds the bridge to the quantum world. If there's a limit to how tightly you can bend the fabric, that implies there's a smallest possible structure, a kind of minimum pixel size for reality. And this fundamental, tiniest scale, the theory suggests, is the real origin of Planck's constant, the absolute cornerstone of all quantum physics. So there we have it, our four ingredients: a 3D fabric with variable density, elasticity, and a limit on how much it can bend. Now for the really amazing part. Let's see how this simple blueprint could potentially build the entire, incredibly complex universe we know. And right here, it all just clicks into place so elegantly. The most fundamental constants of our universe, mass, gravity, the speed of light, Planck's constant, they stop being these mysterious random numbers. In this model, they become emergent properties, the totally natural consequences of the fabric's simple physical characteristics. But here comes the biggest test of all. I mean, it's one thing to explain these big, overarching constants, but can a smooth, continuous fabric actually explain the lumpy, discrete nature of particles? Can it actually build an electron? You see, our standard view of quantum mechanics is all about calculating the probabilities for a system of many different objects. But this fabric theory flips that on its head. It says, no, there's only one object, and what we call quantum physics is just our clever, probabilistic way of trying to understand its super complex local behavior. So this is really the million-dollar question, isn't it? Fermions, things like electrons and quarks, are the stable building blocks of all matter. They are distinct, individual things. So how on earth could a localized knot or a ripple in a continuous fabric achieve that kind of stability and have its own identity?
Okay, so the proposed game plan is to try and create something called a resonance carrier ball. You can think of it as a self-sustaining, stable vibration in the fabric that basically acts like a particle. The author suggests using some specific mathematical tools to model it, but they admit the single biggest challenge is replicating a fermion's bizarre property of half-integer spin. It's this unique kind of twistiness that might, maybe, be modeled by a sort of continuous knot in the fabric, but it is a massive hurdle.
And this is where the author makes a really bold and honestly a crucial scientific statement. They put it all on the line. They say, look, if this stable particle-like resonance cannot be constructed, mathematically or otherwise, then the whole idea is wrong. It falls apart. And that's huge because it makes this wild idea testable, at least in principle. So let's just step back for a second and take in this whole picture. What we're looking at is a vision of the universe not as a collection of billiard balls rolling around on a table, but as the intricate, ever-changing shape of the table itself. So let's just recap the core takeaways. At its heart, you've got this idea of one unified 3D fabric. From its simple physical properties, all the laws and constants we see just emerge. In this picture, particles aren't really fundamental things anymore. They're just stable patterns of vibration. The theory's biggest challenge, its make-or-break test, is proving it can actually form a fermion. And to get there, the author makes a very clear call for more research and for people to collaborate on this problem. And that really leaves us with this final, profound question to chew on. Are we, and is everything around us, truly a collection of countless separate little things? Or are we all just fleeting, incredibly intricate patterns in one single, magnificent cosmic fabric?